Good morning, this is Grand Rapids Community College Calculus class, Calc 2, and we are doing the integration and techniques of integration. And the last class we had two sections we were trying to cover. One which was sort of a summation of the ideas using different integrals. How do you look at an integration and see which type, whether you should do parts or partial fractions, trig substitutions, or what. And then the other one was integration using tables and your computer, your calculator. So I'd like to start with the first one. It's in section 7.5, techniques of integration and strategies. Were there any questions from that section? 23. Okay, so we have this integral 1 plus the square root of x to the 8th power. Again, the various types of integrations we have talked about are U-Substitution. The first thing you want to try is see if you can do a U-Substitution. If you try to do a U-Substitution here, we're let U would be what's under the radical here. The du would have a square root of x in it, in a denominator, which isn't here right now. So unless we could somehow algebraically rewrite this, that's not going to work. After that, we talked about integration by parts. If I was doing integration by parts, I'd want to have this be something where when I could break it into a piece where when I took the derivative, it would get simpler, and the other part I could integrate. Again, when I take the derivative of 1 plus the square root of x, I end up with a negative 1 over the 2 square roots of x, which isn't really going to make it simple. So it doesn't look like an integration by parts either. Partial fractions is used when we have rational expressions, usually polynomials. This doesn't look like that. So what's left? Anybody have some suggestions on this one?
I use U-Substitution.
And if you use U-Substitution as 1 plus the square root of x, and du is negative 1, it's usually 1/2 times x to the negative 1/2 dx. But how are you going to end up with, where'd this come from? Where are you going to get the x to the 1/2 from?
Well,
So you tried rewriting this?
yeah, I did it, but then what I did was I then solved.
So x to the 1/2.
Square root of x equals u minus 1.
Yeah, x to the 1/2 is going to be u minus 1.
Yeah.
So let's see, if we try this way, I can pull a 1/2. I need a 1. Let's try and rewrite this. So I put a 2 in front. I need to be able to divide by the square root of x. So I need a 2. But in order, so I already dealt with the 2. The x to the 1/2, I need to multiply by an x to the 1/2, but that has to stay inside my integral. Okay. So we can do this if I use this substitution. Now, you notice the balance here again. I needed the x to the 1/2 and the 2x to the 1/2 in its denominator because that's what my derivative was. The 2 I can balance out front. The x to the 1/2 has to be inside. So now u minus 1 is going to go here. So integral of x equals 0 to x equal 1 of u minus 1. And this is going to be u to the 8th power. So we get 2 times u to the 10th over 10 minus u to the 9th over 9. Evaluated from x equals 0 to x equal 1. Now, do you prefer going back into x, or do you want me to rewrite these limits in u?
I usually go back to x.
Okay. So I get 1 plus x to the 1/2 to the 10th over 10 minus 1 plus x to the 1/2 to the 9th over 9. And then when I plug in x equal 1, this becomes 2. I get 2 to the 10th over 10 minus 2 to the 9th over 9. When I plug in x equals 0, I get 1/10 minus 1/9. And the 10th is 1024. I don't know that I could actually figure that out in my head. But it's going to come out to, so this is 102, and this is 512 divided by 9, so that's about 50 something. So it's about 50. So it's about 100 altogether. Point something. Is that okay? Okay. So this is one of those particular U-substitutions where we didn't exactly have the du, but we were able to manipulate this to make it look like a du. The other technique that possibly could work, but the limits are going to be ugly, is to actually, even though this is a square root of x, you might be able to do something with trig substitution here. The 1 plus means that I'm going to be using tangent. And so I'd take the x to the 1/4 power equal to the tangent theta and try to work that. I think this was much cleaner. Okay, another one. 31. $41. Okay. Well, you know, it's difficult to hear out here. Okay, so again, U-substitution, if I let U equal theta, that's not going to change anything. If U is tangent theta, then I need a secant squared. It's not partial fractions because this is an irrational expression, but this looks like an integration by parts, possibly. If I let U be theta, then du makes it d theta, and I can get rid of that. The question is, do I know how to integrate the tangent squared? Didn't I do that one the other day? So let's take a look at that. Do I know how to integrate just tangent squared? Because if I'm going to use integration by parts, this would be my dv, and I need to be able to integrate this. The trig substitution, the the Pythagorean substitution for tangent squared is secant squared theta minus 1. And that's what I know. The antiderivative of secant squared is tangent theta. And the antiderivative of 1 is negative theta. And you'd have a plus an integration constant here.
Yeah. There's theta.
Yeah,
There's
hang on.
theta.
So this is my dV.
Yeah.
So when I go to this, I need to be able to know that I can integrate tangent squared before I can use parts. That was the idea, was I need to know. So if I'm going to use parts, then u could be theta, du would just be d theta then. dv could be tangent, my stack's crooked. Tangent squared theta, d theta, and v is what I just came up with, is tan theta minus theta. So uv is going to be theta times tan theta minus theta minus integral of v du Did we do the integral tangent theta the other day too? I think that I told you I would grant you any of the integrals that are on a page a couple earlier, and these might have been on here. So on page 484, it has integral of tan. It doesn't have tangent squared on it, so we would have had to do tangent squared. But it does have the integral of tangent, it's natural log of secant. Oh, wrong way. So I get theta tan theta minus theta squared minus, so the antiderivative of tangent theta was secant, natural log of the secant. And the antiderivative of theta is theta squared over 2. Now I have plus some integration constant. So these theta squareds I can combine. This is theta squared plus theta squared over 2, which is just going to give me negative theta squared over 2. So depending on which order you want to put it, I get theta times tan theta minus natural log of secant theta minus 1 of theta squared over 2 plus some integration constant. Now if I were doing this by hand like I just did, what may be a good way to check my answer? I could try taking the derivative of this, which doesn't look too imposing, and see if I end up with that. So let's take a look. So the derivative with respect to theta of theta tan theta minus natural log of secant theta minus theta squared over 2 plus some constant. The first term I'm going to need a product rule, so derivative of the first times the second is going to be 1 times tan theta plus first times derivative of the second, theta times secant squared theta. Natural log is going to be 1 over the argument times the derivative of the argument, and derivative of secant is secant tangent. Derivative of theta squared over 2 is negative theta, and derivative of c is 0. So here I have tan theta minus tan theta, because the secant squareds go, secants cancel each other and I get minus tan theta. So I have theta I can factor out times secant squared theta minus 1, which is theta times tan squared theta. And that checks. So good. Phew. Is that okay? So again, what would make me think of doing this one by parts is I have a product of functions, one of which, when I take the derivative, gets simpler. Often that's the x or theta or whatever my variable is here, a polynomial version of it. And then the other part has to be something I can take the antiderivative of. Which is why I wanted to check to make sure I knew how to do the antiderivative of tangent squared first. Okay, good. Another one? Last one from that section. Okay, how about the next section? So the next section, there were two different parts of it. One part where you're supposed to try to use the integral tables, and another part where you're supposed to use your computer algebra system, which in your case is your calculator. Did anybody have a question on some of those? 29. Okay. Now when we start to look at these integration tables in the back, there are quite a few of them that have square roots of something. So we're looking for one that has a square root of a u squared minus a squared in or a u minus a in the denominator. So let's see, starting over here. Here's a square root of u squared minus a squared, but the other u's in front here, I kind of want that to look more like it's in the numerator. Square root of u squared minus a squared. So down this side, it doesn't look like there's anything where it's u squared minus a squared. Oh. U squared minus a squared. These are a squared minus u squared ones. So here it goes, forms involving square root of u squared minus a squared. There's one in the denominator. There's in the denominator where a u squared is on top. And that would be good if we had, since we have x to the 10th on the bottom, if there was also x to the 10th on top, that'd be good. We may have to fuss with that to make that work. Let's see if there's another one. Is there another one in there that actually fits what we want? Squared minus a squared. I have a feeling that I'm going to have to make this 43 work. So let me see if that's what it comes out to be. Let's take a look. It's going to have to be one of these ones here because it's 43, 44, 45, something in there, because that's the form of what I have in the denominator. So let's see which one possibly works. So if u squared minus a squared is supposed to match x to the 10th minus 2. Then u would be what? What do you think, brother? Well, u squared would be the same as x to the 10th, so u is going to be to the, what would I multiply by itself to get 10? This would be x to the 5th. So when I square it, I get x to the 10th. Is that okay? So then du is 5x to the 4th dx. So this is going to work because this x to the 4th that's in my numerator is actually going to be part of my differential. And I just need to put a 5 in front and a 1/5 outside. A is going to be the square root of 2. Because a squared has to equal 2. So this does match number 43, which says this is going to be the natural log of the absolute value of u plus the square root of u squared minus a squared plus c. So that's going to be the natural log of u is x to the 5th. U squared minus a squared is x to the 10th minus 2. And we have plus c. That can be, what do you follow that? So let me back up to, I really basically, if you look at all those integral tables, I have two choices for this, what's going to be on the square root. Either this is u squared minus a squared, or it's u plus a. So you have to look at which one's going to give you the derivative differential that matches the numerator. So I started with u squared minus a squared, but that means you're going to have to be able to take the square root of that to recognize u is x to the 5th. If it had been a u would have been x to the 10th here, and then the derivative of that would have still been x to the 9th. That wouldn't match what's up there. Okay. How about another one that uses integration tables? Does anyone have another question? And that's it. $17? Is that what you said? Did you just say yep? Okay, so again I have a square root, and most of those are either a u plus a, or a u minus a, or a minus u, or a squared minus u squared. So what I really have to look at is the part under the square root. I'm going to go kind of off the side here, and so think about how can I rewrite 6 plus 4y minus 4y squared. Now, what we want to do here is actually something they call completing the square. So this is going to be 6 plus, or 6, well, I'll just going to put it in a different order here for a minute. Minus 4y squared plus 4y. I'm going to keep my constant over here and then figure out what I need to do to complete the square. So 6 minus 2y minus, so I don't know if you remember, we're completing the square. If I have something like 4y squared minus 4y plus what is going to be a perfect square, this part has to be 2y, and then the sign has to match the middle term. And then whatever you put here, when you square it, is what's going to go there. And it has to match so that when I take twice the cross product, I get that 4 in there. So if you start thinking of this as some constant like k, I know that when I square this out, I get 4y squared minus 4yk plus k squared. So if 4yk has to match 4y, then k has to be 1. And then k squared is also 1. So that means up here, I should use a different color. In order to have this be 2y minus 1 squared, I need to add 1. But you can't just add 1 to your term. So over here, I'm going to subtract 1. So that the net effect is I have 0. I've added 0. So instead of a 6 here, this is going to be a 5. So negative 1 plus 6 gives me 5. And negative 4y squared plus 4y plus the 1 that I added gives me 2y minus 1 squared. Now wait a second, I got to make sure my sign's right. This is not the right sign. I need to have this in parentheses. So this is actually 7 up front. Be very careful. This has to be in parentheses. And when I factor out the parentheses, this sign, because this is a negative here, all these signs inside change. So it's 4y squared minus 4y plus 1. That's what's going to give me the 2y minus, see the plus here. That's to match that. But when I take the negative sign through everything, these signs have to agree. All right, so let's make sure I did that correctly before I go and use it. 7, and when I square this, I get 4y squared minus 4y plus 1. 7 minus 4y squared plus 4y minus 1 is negative 4y squared plus 4y plus 6. Is that what I started with is my question? And it is. Good. Every once in a while, I'll mess up the signs there, so be careful with those signs. So what I want is this one here. So let me go back to my original one. So I rewrote it in that form where I've completed the square. Now again, we're going to look. This looks like a squared minus u squared sort of format with possibly a u out front here. So I'm going to look in my table of integrals. I want to look at the one where a squared minus u squared is the one here at the top. Square root of a squared minus u squared. And I want to have one that just has a u in front, not a u squared in front. Do they have that? Hang on, it might be over here on this side. A squared minus u squared. There's one in the denominator. I want a square root of a squared minus u squared times u, it looks like, but I don't. Square root of a squared minus u squared. That u is squared here, and I don't really want that. Now you think that this will be, if I take and make u squared, know I can do the integral now using a technique similar to the one that Eric suggested for the first problem tonight from the last section. I'm just trying to figure out why it's not fitting one of the forms that's listed here. There's another possible, since it doesn't seem to fit any of the forms that's listed here, we may have to rewrite it as a sum of, so let me step off the side here again. So if I wanted to, I should be able to rewrite this, again, this is similar to the one that we had this morning, earlier, but I may need to actually go back and redo this. Let's suppose instead what would they say? U plus A? What would they do with this? Let me go suppose instead U is what's under the radical.
I was looking at on 114.
Is there one I didn't get to?
I wasn't able to make it work all the way, but
Yeah, maybe I'm going to try it. That may be what I'm looking for in terms of having to rewrite this. So he's saying like something like this one here. Now the issue with this one is I have to find a U that makes this match so there's no constant term in under the radical. So if I'd have to choose a U, let's see if I can do that. We're going to try to make that match the thing we have. Does 2AU minus U squared match 6 plus 4y minus 4y squared? So again, I know that this has to be, U has to be 2y plus something. So the U squared ends up being 4y squared plus 4yk plus k squared. And 2AU is going to be 2a times 2y plus 2 plus k. 4ay, try that again. So then 2AU minus U squared, it's going to be this one minus that one. It's going to be 4AY plus 2AK minus 4y squared minus 4yk minus k squared. So for this to match, we have the minus 4y squared part. Those match. Which means the y parts also have to match. We'll start with that next. So 4ay minus 4yk has to be 4y. So when I factor this out, I get that a minus k has to equal 1. So a equals k plus 1. Now, if this is going to work, this form, then the other part that has to match is the 2ak minus k squared has to equal 6. So I'm going to sub k plus 1 in there for a. It gives me some choices here for a k. But this is a pretty ugly. I'd have to, let's see, b squared minus 4ac is going to be positive. So I can force this to work where k is -2 plus or minus the square root of 4 plus 24 all over 2. -1 plus or minus the square root of 1 square root of 7. And a is just going to be that plus 1. So I guess I can make it work. It's not a very pleasant one, though. You would think they would have worked that one out in a different form. Let me think about what could I do with that. So I did end up making that work, but I'm not very satisfied with that one. So let's go back and see if I can't do something else with this. So I put a 2 and a 1/2 here. And then if I subtract 1 times that integral, but then I have to add that integral again of that square root. Then I'm thinking this looks kind of like a u times the square root of a squared minus u squared. And this one looks like the square root of a squared minus u squared. But did we decide they didn't have this today? That was the issue. But I know how to do this one by substitution. It just doesn't fit the integral tables. Not very satisfying. That's a problem. But again, we can do it a couple ways. It just doesn't. None of them actually fit the way I would like them to fit. I wonder if they wanted you to do. Let's try one more one. One more format here. if I let u be the whole thing here, then du is going to be 4 minus 8y. So again, I can kind of put a dy. Sorry, don't forget the dy here. I can kind of put a minus 8 here and divide by 8 out front. And then I can add 4. As long as I also subtract it over here. Now, this one on the left we can do as a U-substitution. So I end up using, I can make this where I'm using 2 different ones. This becomes negative 1/8 times integral of u to the 1/2 du. And here, I am going to actually try to rewrite it as the a squared minus u squared part. That one fits one of those formats. It's on 30, so it's number 30. I guess it's a little better, but still not as nice as I would like it. So I need a 2 in front and divide by 2 inside, outside. One of the things I don't like about this setup is I've used u in 2 different ways. I think I mentioned that before. I have the same letter representing 2 different things. I'm not a real big fan of that. And over here, according to number 30, yeah, I did that already. It should be this u over 2 times is the same thing. So it's 1/4. It's the square root of the same thing we had. Plus a squared over 2 times the inverse sine of u over a. And this part I need to figure out. This would be negative 1/12 times 6 plus 4y minus 4y squared to the 3/2 power. Try to simplify that whole. So I have negative 1/12, 6 plus 4y minus 4y squared to the 3/2 power plus 1/8 2y minus 1 times 6 plus 4y minus 4y squared to the 1/2 power plus 7 over 2 times the inverse sine 2y minus 1 over the square root of 7. I don't know. It worked a couple different ways, but none of them were as satisfying. We could have almost done this without using a form of that U-sub, without using the tables, and easier. So, but let me go and see and when it gets this complicated, you're never sure whether doing it by the calculator is going to give you a form that's going to be even more difficult to match to the one you have. Let's try that. So I'm going to do the antiderivative of the square root of, excuse me, I need y first. Y times the square root of 6 plus 4 times y minus 4 times y squared with respect to y. Square root of 2 times 2y minus 1 over 8. Looks like they've factored some of this out. We have a 2y squared minus 2y minus 3. So 3 has power. So they took a square root of 2 out. Do have an inverse sign of the same argument, 2y. Oh, sorry, you guys can't see what I'm doing. They do have the inverse sign of the same argument, but the coefficient's not quite the same. And here it looks like they took a square root of 2 out, so instead of having 4y squared and 4y and 6, they have 2's and 3's. So that's what explained that square root of 2 in both of these numerators. And if I added to have a 2 up on top, that would give me a 12 on the bottom here, which would then match that front term. But this one doesn't exactly. It does have the 1/8 part. And it's pretty close. 1/8, 2y minus 1. Everything matches except these 7/8, and I only have 7/2, which means I very possibly left out something here. So let's look at my constants up here. So I had to add a 4 here to get my minus 4/8, which means I have to have plus 4/8 over here. And when I try to make that into the U format, U should be 2 dy, so I need to put a 2 in, which means I need to divide by 2 out front, so I get 2/8. And then, according to the formula number 30, it's a squared over 2, so I get 7 over 2, and I forgot to multiply it by the 1/4 here. So I left that term out here, so it should be 7/8. So it did all match, but just like I said, it's not a very pleasant match. Okay. I will try on tests not to give you anything like that. Again, typically on the test, what I'm going to say is I've tried to let you know, again, it's still a couple days away, but I'll probably have like 10 integrals sitting out there and ask you to do one by parts and one by substitution, one by partial fractions, one by trig sub. So you get to choose. And if there's one that looks particularly ugly, don't do that one. Find the one that matches a little better. On the other hand, as I probably mentioned before, it is very typical when you're actually in a job using mathematics, for it to take a while to wrestle with something and have it not be as pretty as all that. So sometimes things do get a little uglier. Which is why the other part of this section, I don't know if anybody has any questions from that, using a computer algebraic system is very common in the workplace if you really need to use calculus. So, did anybody have any questions about the ones that involved using a calculator? You guys all feel comfortable using them? Okay. So let's brings it to the next section. So the next section is going to talk about numerical techniques. And we use numerical techniques in two situations. So the first situation that people use numerical techniques is we have data, but we don't really know what function. When I say well-defined function, I mean I can describe the function, but it's not defined in terms of the trig functions and logs and exponents and polynomials that we have. So we might have lots of data out there measuring something like the temperature of an engine block or something like that we haven't been able to fit to a model that works consistently. Let me put model. So in that situation, but we still want to figure out the antiderivative, then we might use numerical techniques. The other situation is there are still some functions for which we don't know the antiderivative. Classic one comes from the bell-shaped curve, something like e to the x squared dx, for example, or ones where it's the square root of 1 plus x to the 10th kind of thing. We don't really have a specific way to find an antiderivative every time. There's really a third case, and the third case is ones like I just did, where finding the antiderivative is unpleasant, but you really just need a numerical value. Then we might use numerical methods. So that's what we're going to do this section, just to remind you how to do them. So, for instance, I might have a function like this one. Now, way back last semester, when we first talked about antiderivatives and said they were a definite integral was equal to the area under the curve, what was our first approach at finding that? Was to make rectangles. And one set of rectangles might have been ones where we added up heights of the rectangles from the left end. You guys remember doing this? So if I was trying to use this technique to find the sum, find the area, find the antiderivative of sine of e to the x from 0 to 1, what would I need to do? Well, I'd need to find the value of my function at the left endpoint of every one of these rectangles and then add those times the width of my rectangles. So let me go back and remind us. We call this a left-hand sum. Your book refers to it as L sub n. So we are going to add up the function values, which is the height of our rectangles, times the width of our rectangles, and this is assuming that all our rectangles are equal width. And the width of those is going to be the right endpoint minus the left endpoint divided by how many rectangles. Now, in the homework, you're going to be asked to get 6 decimal place accuracy, which means when you're taking these data points, you're going to need more than 6 decimal places. In fact, I kind of recommend like 8 or 9 decimal places, so that if you add up 10 of them, you're not going to be off by more than 1 decimal place less than. There's rounding error. And if you make your rectangles, and those of you that might go into a computer science kind of major where this might be an issue, you do have to watch out for the rounding error of that. Your even best computers only use so many decimal places when they're doing it, and when you subtract, they can cause quite a bit of error if the values are close to each other. So for the left-hand rectangles, I wouldn't use this value at 1, but I would have used all the other 10 values, add these up, and multiply them by 0.1 because the width of my rectangle is 0.1. Does that make sense? So I'm going to do that once here. So in our particular, for our function, x of 1 is 0, and is 10. Delta x is 1 minus 0 over 10, is 1/10. So I'll just take my calculator and type these in. Now, so you can see, you can guess that tonight there might be a little bit of tedium in terms of figuring out, typing in all these decimal places and not messing up when you type them in. There are ways that you can use a table of values rather than not the table, but use a list and have the calculator sum the list for you. So I got 9.350530011. If I want 6 decimal places of accuracy, I'm going to get 0.935053. Now, does that seem reasonable? Again, I recommend drawing a graph and looking at it and saying, okay, if I were to make one big rectangle, the width would be 1, and the height would be 1, and so the whole area would be 1, and it's a little less than that. So the fact that I got 0.935, that seems reasonable. Now, do I think that estimate is too high or too low? Well, in this case, it looks like more of my rectangles over here are too tall than the ones that are over here that are too short. So I'm thinking that my estimate here is a little too high. So the other technique was use the right-hand sum. Now the right-hand sum is going to use the right endpoint for the height of the rectangles. Everything else is going to be the same, but it does make it so that these rectangles on the right side, where my graph is decreasing concave down, they're all going to be underestimates instead of overestimates. So right-hand rectangles look like left-hand rectangles. The only difference is going to be the subscript. So instead of x sub I minus 1, it's going to be x sub I. Delta x is the same, the number of rectangles will be the same, everything's going to be the same. So in terms of what I'm doing here, instead of not counting 1 as one of my function values, I'm going to include 1, but I'm not going to count 0. So if you were actually summing these, rather than go back through and add them all up again, I recommend taking the last answer you had, subtracting 0.84147, and adding 0.410. Shut that from here. So I could take my last sum, add the right endpoint, subtract off the left endpoint, and you get your new sum. It's a little easier than adding all those again. So I still have the 0.1 as the width of the rectangles, and when I add up the sum this time, I get 8.919840317. Which gives me 0.891984. So now when you look at those two answers, you say to yourself, perhaps, why do I have 6 decimal place accuracy when these are only agreement to the first decimal place? Can't I get a better estimate? Now, my guess when you look at this one was that the left endpoint was too high, and the right endpoint is going to be too low, so how about we average them? So I'm going to add those two and divide by 2. Now if you think about that, it can be thought of as 1/2. Now, when I start at the left end, this is going to start at x0. That one's not going to start till x1. Then all of them, the rest of them are going to have the same values, except at the very end, this is going to stop at n minus 1, and that one's going to stop at n. So we sometimes rewrite this as delta x over 2 f of x0 plus 2f of x1 plus 2f of xn minus 1 plus f of xn. So all the middle terms have a 2 in them. The left endpoints only have 1, and it's delta x over 2. Let me zoom in a little bit, because it's blurry to me. So f of x naught, but then it's 2f of x1, it would be 2f of x2, all the way down to the next to the last one, 2f of xn minus 1, and then the very last one, there's only one of those. That's what I'm going to get when I add these together. Now it turns out we call this the trapezoidal rule. And the reason we call this the trapezoidal rule is because this formula actually, if you think about it in a different way, if you separate these out into pairs, you can have f of x naught plus f of x1 times delta x over 2 plus delta x over 2 times f of x1 plus f of x2, and so on down the line. This is the formula for a trapezoid. Add the two bases and multiply by the height over 2. So even though I was originally conceiving this as the average of left-hand rectangles and right-hand rectangles, geometrically that ends up being the same thing as if we connected trapezoids to the endpoints. So it looks like something like this. Now, especially over the TV, that looks pretty dead on. It's not, but it looks pretty close. There's a few spaces where you can see that I've connected. Essentially, I take the two endpoints here and connect them with a line segment. So the only places where you see any difference is where there's a significant curvature. So I tried to zoom in a little bit to get a feel for that. So I'm just looking at the very top of the middle ones, and you can see that here the trapezoid is going to be a little bit of a lower estimate, but it's going to be a decent estimate. Okay, it's very close to the curve, much closer than either of the other ones were. Okay, so backing up, if I've already done the two of these, in this case, it's going to just be, now, again, please use more decimal place accuracy and then round off after you add them. So let's see if I can't get us to do this on the calculator though. So the first thing I'm going to do is go to y equals, and I've typed mine in already, sine of e to the x. And the second thing I'm going to do is I'm going to go back to applications, and I want to go to my, not to the table, but I want to go to a stats list, or some of you, if you don't have that, I think have a matrix, data matrix, something like that. So I'll do a new one. Data. Is this going to work? Okay, so we're hoping this works. So let me try just for a couple of them here. Point, we're going to start with 0 and R1C1, and then 0.1 and R2C1, and 0.2. I'm going to stop there before I type them all in and see if I can't go up here to C2 and make C2 equal to Y1 of C1. Good, so it worked. Now I'm going to, so that means I'm going to extend this down until I go to 0.4, 0.5, 0.6, 0.7, 0.8, and 0.9. Okay, so my left-hand sum should be the sum of C2. So I want to see if I can do that now. Let's go to F5. I just really need the sum of, oh, I don't know, C2, C2. No, that's good. So it added up. Now that didn't get what I got last time. So it's perhaps I added them wrong on my calculator. 0.893975. Anybody happen to check my work last time? No. Well, looks like I might have done it wrong. So this summation x should be the sum that I get. X bar actually is the average, but it's divided by 10, so it's the same as my summation x to 8.939749. That would be my left-hand sum. Now, if I want to, I can then, to do the right-hand sum, I can add 1 here. Oops. Quite interesting. And delete the 0 at the top. Okay, good. And then I can go back and do my calculation again. One variable, summation of C2, enter that, and this would give me 8.5. Oh, 059. So different values than I got last time. So let me fix those. So my right-hand sum, supposedly, right-hand sum was supposed to be 0.850906. And my left-hand sum, I forgot to write down last time. And again, to find my trapezoidal rule, I would add these two and divide by 2. Okay. Now, supposedly the actual value to more decimal place accuracy is 0.874957197. Now you can see that my left-hand sum was too high, right-hand sum was too low. Trapezoid is a better estimate, but it's still a little low. And how accurate this is the difference here is about 0.0025. We call that the error. Now, there are rules about the error that we can figure out, and your book gives us a formula. So for the trapezoid rule, we're going to call it E sub t for trapezoid. It's equal to kappa times b minus a cubed. I should say it's less than or equal to. So this gives us a maximum value for our error over 12n squared. And kappa is an upper bound for the second derivative. So if we're trying to figure out what our error should be, I know we ended up with 0.0025 about, but if I want to look at my function value, my function was sine of e to the x. So the derivative of that is cosine of e to the x times e to the x, and the second derivative of that is negative sine of e to the x times e to the 2x plus cosine of e to the x times e to the x. Now if you look at this, you can say, what's the maximum value of this going to be? You can ask yourself that. Now, how do we, so we could actually take some time here, calculus-wise. How would I find the maximum value of some function? You guys remember this from Calc 1? Yeah, take the next derivative of this. So if I want to find the maximum value of my second derivative, I'm going to take the next derivative again. At this point, I may want to try and use my calculator to take the derivatives. So let me go back through my derivatives here. Show you what I'm doing. So I'm going to differentiate my answer with respect to x. So that's my second derivative there, and I'm going to want to do that one more time. So this gives me my third derivative, and then I'm going to want to solve that. So I use algebra here. Solve that the answer equals 0 for x. Now, if we look at this, there's a chance that this actually doesn't ever equal 0, but because why? What am I trying to maximize? Well, I guess it should have a max. It should have a 0. So, trying to maximize my concavity. Let me think about that. Does the concavity ever change in this function? Let's look back at it. While my calculator is spinning its wheels, let's take a look back at my function here. This function is concave down the entire time, and the concavity seems to be getting more negative the entire time also, more curved. So it may not end up on my interval that I have a maximum concavity somewhere in here. So my calculator finally finished spinning its wheels here. And I get x equals 16.7 or 16.8, x equals 2.1, and then it says some more over here, or x equals 1.7, or x equals 0.926. There's one that is on my interval, or x equals negative, and that's it. So 0.9260573, I'm going to want to keep that one. Let me write that down, 0.92605734761.4. So at that point, I need to figure out what my f double prime is approximately. Now I could have overestimated here, and just what do I know the bound on sine is? Sine's always between -1 and 1. Cosine's always between -1 and 1. So I could have bounded these and said this is as big as it's get is going to be 1. The biggest this gets going to be 1. The biggest e to the 2x and e to the x get on my interval are at x equal 1. So I could bound this and say it's e squared plus e, which is going to be 10 about. But I'm hoping I get a little better estimate here. So I'm going to try f double prime of 0.926 approximately. I'm going to use my calculator actually to store. Let me go back in here. My 0.92605734761.4. I'm going to store that in a letter.
I think you got too many zeros.
I probably do. And I wouldn't even know because it's in the fourth decimal place. I probably wouldn't even notice. But I'm going to store this in some letter like C. And then I'm going to try and find my second derivative of C here, which was negative sine of e raised to the c times e raised to the 2 times c plus cosine of e to the c times e to the c. Let me double check and make sure that's what I got. Yep. And then I use an estimate there. So instead of a 10, I got negative 5.7. Okay. So I can use k as approximately 6. Again, it's the absolute value. So in our case, it was a negative, but I'm going to use k as approximately 6. And we had, so 6 times 1 minus 0 cubed over 12 times 10 squared. is 0.005. So I know that my error based on this trapezoidal method should be less than 0.005. And in fact, we got something that was about half of that. So this is an upper bound. Okay, so there might be a question where you're going to be asked to do something with this error term. How many, so the next question I could ask, still working with trapezoidal rule, might look like something like this. How many rectangles would I need to use? Using trapezoid. And I'm going to stick everything else the same. So my kappa is still going to be about 6. And b minus a is still going to equal 1 minus 0, which is 1. So I want k times b minus a cubed over 12 times n squared to be less than or equal to 0.0001. Multiplying the n squared to this side, I need n squared has to be greater than or equal to 1/2 divided by 0.0001. So n squared has to be greater than or equal to 500. 5,000. So n has to be greater than 70. N is an integer, so I mean a whole number even. It's the number of rectangles we're making. Okay, so backing up. Trapezoidal rule. So trapezoidal still fits kind of what we had done up to this point. We had done left-hand sums, we had done right-hand sums, and then to get a better estimate we had used the average. There are two more techniques we wanted to talk about, one of which is called the midpoint rule. Now it turns out, let me see if I can find a picture I want here. The midpoint rule instead of using the endpoints, is going to be the summation I equal 1 to n of f of, and we're going to call it x bar sub I, because it's the average delta x, where x bar sub I is x sub I minus 1 plus x sub I over 2, the midpoint of the ith interval. Now the inconvenient thing about this for us when we're calculating these on the homework set tonight is on my list, these midpoints aren't the ones we've already calculated. So on the interval from 0 to 1, the midpoint, 0 to 0.1, the midpoint is going to be 0.05. And between 0.1 and 0.2, the midpoint is going to be 0.15, and so on. Now we calculated each of the endpoints, so it was easy to go from a left-hand sum to a right-hand sum because almost all the points were the same. But with a midpoint, I'm actually going to have to calculate 10 new values. So backing up to my calculator here. My data is still in my list, I'm hoping. So I go back to my apps, over to my data matrix. Exit variable. I lost it somewhere. I must not have saved it. So I'm going to use 0.005, 0.05, 0.15, 0.25, 0.35, all the way down to 0.95. And then C2, to get it to calculate all those, I go up to C2 and then type in Y1 of C1 and hit enter, and it calculates all those values for me. And then to get it to add the sum, I go to the calc menu and do one variable stats, not two variable stats. Tell it to do it on C2. And when I hit enter, it gives me the sum as 8.762161, and my delta x is 0.1. So I'm going to write that down over here. Again, you may remember or may not remember. What I said the exact value was. So to 6 decimal places, it was supposed to be 0.874957. And so now we're off by, instead of 0.0025, it's 125. So it's about half as much error as we have with the trapezoidal rule. Now it's sort of an interesting thing to look at. See if I can get one of these here and draw it out again. Where's that? There we go. Here's my midpoint rule. But in my midpoint rule, you can actually think of these as trapezoids, but instead of connecting the two endpoints, the trapezoids are parallel, or you can make them whatever slope you want, as long as the left endpoint and the right endpoint are equal spaced. So you can actually make them kind of like tangent to the midpoint of your intervals. So on the one that we could see it best, just if I can draw it well enough. This is approximately a midpoint, and I'm making like a trapezoid here that's a little bit too big because it's concave down compared to the trapezoid that we got with the trapezoid rule that was too small. Now it turns out, if I had to blow that up a little, that a trapezoid that connects these endpoints versus a trapezoid that's sort of parallel at the ends I should have stopped here. Huh? It turns out that this amount of error above is less than, typically less than the error below. Now it really depends on your function, but in terms of the way we can prove what the error is, we're about twice as accurate if we use the midpoint rule as we are if we use the trapezoidal rule. In fact, the error term is exactly the same, just with 24 in the denominator instead of 12. So equals less than or equal to. I'll use M for midpoint. So it means you could use fewer rectangles and be just as accurate. So in terms of space, I could use square root of 2 fewer, divide by square root of 2. So instead of 70, I might be able to get the square root of 2500, which is like 50. So I can save myself a few rectangles. Now it turns out we're going to do one more technique. And this one's called Simpson's rule. And the error for Simpson's rule, I'm going to write down here since I'm on this page already. Has a couple different features. Trapezoid and midpoint are of the same order. That's what we call it, when the n is to the same power and even the interval is raised to the same power. But Simpson's rule has n that's the fourth power, so it closes in a lot faster. And instead of dividing by 24, we're dividing by 180. So the error with Simpson's rule, it's much, much less. Now what we're doing with Simpson's rule is we're going to use parabolas instead of trapezoids. So we're going to connect parabolas together. So if I had 2 endpoints, if I had 3 points, I can connect a parabola through any 3 points. Now it turns out, and I don't think I'm going to have time for this, that if I call this y0 and this y1 and this one y2, and actually by y I mean the y values here. So this would be actually x0 and x1 and x2, and these are the y values. Turns out that the area, what we're trying to approximate is the area under this curve, and if it were an actual parabola, the area under the curve, I'll call it A. Delta x. It should be delta x over. If I do delta x, I think it's going to be over 6. Now, I only use 3 points here. So it turns out you can get a parabola, the area under parabola, by taking the left endpoint and the right endpoint, and 4 times the midpoint. It's kind of an interesting little formula. And then we're going to do the same thing and connect the next couple points, and the next couple points, and the next couple points. So our sum is going to look, remember how the trapezoid one looked. Our area is going to be, so the, what do we call it, Simpson's rule. another sort of an unusual pattern. It goes 1, the coefficients are 1, 4, 2, 4, 2, 4, 2, 4, 2, and at the end it goes 2, 4, 1. So both the endpoints are only counted once, but then every point after that is going to alternate. So it's 4 and 2, and 4 and 2, and 4 and 2 until you get to the end, and it's 2, 4, and it stops. Now, that means in order to do this, that n has to be even. So that we actually end up with the right number of rectangles, a pattern, that 2, 4, 2, 4, 2, 4 pattern. It has to be even. All right, so let me see if I can figure out. I got my calculator to do this. This time it give it to me. Good. Except I don't want the midpoints again. So I want 0, 1, 2, oh, try again. 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, and 0.9, and then 1. Okay. And now over here in C3, I'm going to see if I can't do this. So this one, I want to equal C2, R1, C2, R1, C2. Let me do that. How about C2 of 1? Yeah, it didn't let me do that. I don't know if I like it that way either. Let me go back here instead. Let's try. So I want this one to be sine 1. That's okay. But this one I want to multiply by 4. So let's try this one. Make this equal. It's not even letting me do this, huh? Why isn't it letting me edit this? It's not letting me do that. All right. Well, let's start over here on the right. Equals y1 of z1. That's not letting me do that either. Escape. Get me out of here. Oh, it's not going to let me do that. I'm going to have to use my stats list, which is a little different. Let me try and see if I can get this to work. Y1 of list 1. No, it's not going to let me do that. I'm just going to have to make a table, it looks like, sadly. So let me go back to my data because I have them there. It wouldn't let me do it. So I'm going to use my data. Actually, I have it in my table here. So I'll just write it out here real quick. I know class is over here. So my multipliers are, this one's times 1, this one's times 4, this one's times 2, times 4, times 2, times 4, times 2, times 4, times 2, times 4, times 1. Find what those values are, add them all up, and then multiply them by 0.1 over 3. This is supposed to be delta x over 3. And get your estimate for Simpson's rule, which is going to be closer, but we don't have time to do it right now. All right, so try those. Homework for that set. I don't think they typically had 10 points. I think they're more like 6. So, all right, and I'll see you guys out there tomorrow. I didn't get to drive Simpson's rule. I ran out of time. It's in the book, though, if you're interested in how they get that